Hello everyone, my name is Coscoms and welcome back to another video on the Coscoms channel, where today I will be explaining the Doppler effect and redshift. Excuse these terribly made slides, but yeah, I thought it'd be quite fun to, I guess, do something new on this channel. So, basically, we're just going to start with talking about the, I guess, just wave equation first. So as you can see, we have v equals lambda f, or wave speed equals wavelengths times frequency. So this is your like standard wave equation. If you get any questions, this is usually the one you're gonna, I guess, use, I think. So for example, we have a practice question here. If you have a wave of frequency of 14 hertz and has a wavelength of 3 meters, or what speed will this wave travel at? So if we just use the equation again, v equals lambda f, we get lambda is 3 meters and frequency is 14 hertz. So it's 3 times 14, which give us 42 meters per second, which is our unit. So as you can see, it's pretty simple because it's just simple multiplication. Sometimes they'll reverse it and maybe they'll say the speed is 42 meters per second, and they'll get you to find the frequency, and basically it's just 42 divided by 3, and it's the same equation, and this is like the simple part of what I'm going to explain today. So with the equation, you can actually sort of go through the theory of the Doppler effect. So as you can see, I have this very weirdly made slide I did earlier today, and basically this is the Doppler effect. Now as you can see, we have a ambulance in the middle, and it is going towards the right. It's facing the right, it's going towards the right, and there are two people. There's a person behind it on the left, and there's a person on the right, which is in front of it. And as you can see, I've put some circles around, which show like the waves of the sirens of the ambulance. Now, as you can see, on the right is going towards the person, and as you can see, the lines are closer together, which shows that there is a higher frequency. As you can see at the back, it's sort of wider, which shows that the frequency is lower and the wavelength has actually gotten longer. And how do we know this? If we go back to our equation, which I've put on the top right, v equals lambda f, as frequency is increased, then the wavelength will decrease, assuming that speed is the same, and we know that speed is the same in this scenario. So say on the left, if the wavelength increases, then we know that the frequency decreases. And basically, if this was in real life and there was an actual ambulance going past you, hopefully not going to hit you, because that would be real bad. But say there was an ambulance going past you, and basically as it got closer, the frequency will be higher, and therefore it will actually be louder, you can hear it more, and that is why frequency is also pitch. So higher frequency equals higher pitch, lower frequency equals lower pitch. And I think that is pretty self-explanatory. I mean, you probably get questions similar to the one earlier, maybe, and I think it's a pretty simple concept to understand, I think, and I think this shouldn't be, I guess, too complicated, I don't think. Now, if we move on to redshift and stuff, so as you can see, my next slide, which I've already hinted at, this is the continuous spectrum. As you can see, it is just a gradient of blue on one side, on the left, and red on the other side. And basically, the whole concept of this is if you shone white light into a prism, and light will be refracted at their different wavelengths, and red has a longer wavelength, and violet or blue has a shorter wavelength and higher frequency. And as you can see in the prism, they're all refracted differently, and that gives you a continuous spectrum, as it's like a continuation of color just from one side to the other. And it's kind of cool. But the one we see, I guess, in redshift is the absorption spectrum, which is the one I've shown on screen now. As you can see, there are black lines on the spectrum. They look sort of similar to the continuous spectrum, but now you must be wondering what this spectrum is different and what does it show? Because the main part of this spectrum actually are the black lines. Now you're probably thinking, what are the black lines? And that is a very good question, because that was the same thing I was wondering when I first learned this. So basically, gas absorbs light at specific wavelengths, and those wavelengths are where the black lines are shown on the spectrum. Every element produces a unique pattern of spectral lines, so from the lines we can actually tell what elements are present, and the elements are the gases which absorb the light. So how can we use this in, I guess, a space scenario? So if we were looking at a star, the sun, and we took a picture of this, imagine this whole spectrum here is from the sun. Say maybe this line shows that helium in the outer atmosphere or outer layer of the star has absorbed that spectrum of light, and we know, hey, there's helium in that star, and that's kind of cool. And usually you probably be told which gases are absorbed or which gases absorb which wavelengths, and you sort of have like multiple pictures, and you just compare this line matches that line, so we know this absorbs that, and so on. So that's basically the absorption spectrum. I guess in a quick summary, nutshell, hopefully that makes sense. But the whole juicy part of this thing, or this topic, is the redshift and the blue shift. Now, as you can see, there is a very interesting diagram on the screen here, and there are three layers. One, we have the redshift at the top, we have the rest in the middle, and the blue shift at the very bottom. Now, you must be wondering, what is the rest? So, for example, if we went and took a picture of maybe a star or the sun, we'll see maybe the rest. Or maybe it's a distant galaxy as well. We'll say maybe there's a distant galaxy and we took a sample of what it looked like, and boom, we have the thing in the middle. If we went back again after a while and took it again, or took another, I guess, sample, it'll either be the one on the top or the one on the bottom. Now you must be wondering, what is the difference? Now, as you can see, the redshift, you can see by the lines have shifted at the top towards the right, showing that the lines have gotten further away, because from earlier we can actually see how red is a longer wavelength. That was from the continuous spectrum we mentioned earlier, and here we can see that it's shifted closer to the right, showing it's red shifted and it's moving further away. For the blue shift at the bottom, you can see that it's moved closer instead, and basically it shows that it's blue shifted, it's moving closer, and probably if we took another, I guess, sample again, it will shift even more to the left, and you'll see the black lines just keep moving that way. We can actually use this. I have this diagram here as well, and it actually shows, I guess, how far away a galaxy is compared to ours. So we have the spectrum lab tree reference at the very bottom, and a nearby galaxy is sort of closer, but it's sort of shifted a bit, and then a very distant one is like way out to the right. And I think this is kind of cool. I mean, comment below if you think it's cool. I think it's kind of cool. And as you can see, the scale at the bottom, it shows a wavelength in nanometers, which is a unit we'll be using in a second. So basically, what does, I guess, this actually tell us about the universe? So you can see a very distant galaxy is sort of like very far from us, it's very distant, and we can tell this from the wavelength. And as the wavelength is increasing, we know that, it's getting further and further away, and it actually shows from the Big Bang that the galaxies are sort of drifting further apart, and the galaxy or the universe is actually expanding, and we can use this as a theory, or it supports the theory of the Big Bang, as everything sort of expanding from a singular point of time, which, as I mentioned, is the Big Bang, and it's constantly expanding. From this thing that I've put on the screen here, you can see that the temperature as well on the bottom is in Kelvin. It's really hot at the start, but it's gotten really cold now. Or it's gotten cooler. I think I shouldn't say really cold. It's gotten cooler. I'll use it comparatively because that's better. But basically, I won't go into explaining what like quarks are, photons, all that kind of stuff. That's like overcomplicating things. But this diagram is like a good, I guess, understanding of the Big Bang happened and the universe just expanded from that point, and it's still expanding to this day. So if we look at this equation, we have change in wavelength over wavelength equals speed of recession over speed of light, and this is the wave equation for redshift of EM radiation. Now, you must be wondering, what is this and why are we using this? So if we have a problem here, for example, what is the speed of galaxy B relative to Earth? And we are given the speed of light, which is 3.0 times 10 to the power of 8. So we are looking for the speed of a galaxy, and basically we're looking for how fast it is moving away from us. And we can use it from like looking at the spectrum to seeing how far the lines are moving, and that will be the change in wavelength. But instead here we are given the table, which actually just gives us the wavelengths, and we just subtract to find the change in wavelength. So we would go like that. 657.81, which is the wavelength of galaxy B, minus 656.45, which is the laboratory sample which we were taken, or which we have taken. So we get 1.36 nanometers, which is the change in wavelength, and if we just use the equation again, we get 1.36 over 656.45, which is the laboratory sample, as I mentioned, equals the speed of galaxy B over the speed of light, which is 3.0 times 10 to the 8. So finally, if we just rearrange the equation, we get 1.36 over 656.45 times the speed of light. And for some reason, I didn't show the answer, but the answer is 621,524.87. I just did some quick maths there with a calculator. Definitely not in my head. But, boom, thanks for watching. I hope this was an interesting video, and if you enjoyed, do consider liking and subscribing. And as always, this is Cons blasting off, and I'll see you in the next one. Peace.